All right, so welcome back to another fun-filled week of physics. Um, Want to just go ahead and start letting you know, first of all, that I did grade exam one, and I think I want to go over it with you guys first, just talk about some of the common issues. Um, Hopefully you were able to read my notes and my comments and figure out what I meant, but in case you didn't, let me go ahead and go over that first, and then we'll go over homework questions and then move to new stuff. So for the exam, number one, excuse me, the one that was the rotating door, the biggest issue with that was finding the moment of inertia. Because the moment of inertia of a door, of a rectangular plate, so here's our little rectangular guy, and if we're rotating it about an axis that's on its side, then the moment of inertia is 1/3 m times W squared, where W is the width of the door. So I know a lot of people went with the 1/2 or other variations, but it does need to be 1/3. And that's a characteristic of this rectangular shape. If you actually do the calculus on it, break it down into all the little pieces and add it up, you get that as your moment of inertia. So that's the first thing that was a bit of an issue for folks, is you were calculating the wrong moment of inertia. The other thing that happened was in the calculating of the mass, because what I told you is its weight was like 750 newtons. So the mass is actually equal to that 750 divided by 9.8. So you got to make sure that you account for that as well. But other than that, you guys did fine. You use the torque formula, figure out how much torque is going on, and then divide by your I to get your alpha. So what you should get, the actual answer for this one is alpha is 3.54 radians per square second. So, all right, so that was issue with one. Number two went pretty well overall. A couple of you forgot to differentiate though. So this one, since we're told that theta is equal to 0.3 t squared, theta is a function of t, which means omega is its derivative, and alpha is the second derivative. So you're going to get formulas for each of these that then you use to calculate things. So like for part A, you need to know what's the angular velocity at 5 seconds. Well, you plug 5 in there and you get 3, and then use that to figure out your V and so on. So you guys have the right idea once you calculate or got a number, but since this thing varies with time, we need to differentiate. All right, so then number three was the probe that we're sending to Mars, and we were looking for the total energy. So the total energy, there's going to be kinetic plus potential. And so if we break those down, the kinetic, it's 1/2 mass times velocity. So its mass was 690 kilograms. Excuse me. But the velocity, that one we had to convert to meters per second because I gave it to you in kilometers per hour. So if you convert it, it's 3,333.3 meters per second. So if you go ahead and run those, you get 3.49 times 10 to the 9 joules. So about 3.5 gigajoules of kinetic energy. So then for the potential energy, now this one we can't use mgh anymore because we're far enough away that it actually matters. And the potential energy, that's equal to negative g me times m over r, where m is the mass of the Earth. So if you put those numbers in, Mass of the Earth. I know I didn't supply it, but I also know you guys have access to things like Google and whatnot. So everybody, I think, pretty much found it. So that's 5.97 times 10 to the 24th kilograms. Again, multiply by the mass of our space probe. And then in terms of the R, it's not just the distance away from the Earth. And we are going to take the 2.87 times 10 to the 9 meters. But we also need to add to that the radius of the Earth. It turns out that it doesn't really affect it much. It's only, you know, a few decimal places down, since it's a factor, an order of 3 greater. But technically we need that there, so it's good to just keep that in mind. So you run the numbers on this and you get negative 8.7 times 10 to the 7 joules. And it is negative. The way that we define potential energy, it's 0 far away and gets more negative as we come in. So then you combine those and you get your total energy. If you take 3.49 times 10 to the 9th and subtract 8.7, that's pretty much the 0.9 bit. So you get 3.4 times 10 to the 9 joules. So some of you added that, which brought this up to 3.5 something. But the potential energy is negative. Okay. For 4 and 5, those were the conceptual questions. I may not have them in the right order, but I think number 4 was the elephant bones. They're made of the same material but are wider. And why does that work? Really what I was going for is that if they're made of the same material, then they've got the same strain. So they've got the same modulus, which means to allow for the same strain, they need the same stress. And stress is force per area. So since an elephant is much more massive, it's going to need greater area to end up having the same stress as that of a human bone. So I was looking for something along those lines. And then number 5, trying to remember which one that was. It'll come back to me. I'll think of it in a second. Oh, that was the washing machine, I think. So the idea with the washing machine is as it's spinning, it's getting a much greater angular velocity, which means it has much greater centripetal acceleration. Because it's got greater centripetal acceleration, the objects are trying to get thrown out more. And that's the water. The water gets thrown out through those little holes because of the greater centripetal acceleration. All right, so something along those lines for number 5. Okay, number 6, the diving board. For the most part, this one, okay, the biggest issue was actually the weight of the diving board itself. So if we look at this, there are really 3 forces acting on it. There's Larry out here at the end. Thought you guys would appreciate seeing Larry on your test. There's our pivot point. We have the force that's being applied over here that we're trying to calculate, but then there's also the weight of the diving board that's pushing down right here. So there are 3 forces which give 3 different torques, and we need to balance those. So in terms of the distances and everything, this was a length of 1 meter from the end to the pivot point. It was 2 meters all the way out to our diver. And then the center of mass, since I told you that the board, assume it's uniform, we know that that's going to be exactly in the middle, which makes this 1/2 of a meter. It's 1/2 a meter away from the pivot. So the balance of those torques means that we'll call this force, say, F. We're going to get 1 times F. That's going to have to equal 1/2 times the board weight plus 1/2 times the diver, or not 1/2, sorry, 2 times the diver. So that gives us 1/2 times the 280 newtons for the weight of the board, and 2 times 500 newtons for the weight of the diver, which ends up giving us 1,140 newtons. So that's the force that's necessary on that guy. All right. And then there was number 7, and I have to apologize. I forgot to give you one piece of information. I meant to tell you the velocities of one of them afterwards, because without that, it's actually impossible to do this question unless you do what like 90% of you did. Actually, I think everybody did, is you assumed that it was an elastic collision. And then in that case, our energies conserved. So let me kind of show you the setup for that one. But like I was saying, I meant to have it so that I gave you a velocity of one of them afterwards. So like we got this 10 kilogram thing that's moving at 0.4 meters per second. We got the other one coming in, it's 30 kilograms, moving at 0.2 meters per second. And so what we get from conservation of momentum is, let's go with, to the right is plus. Then we're going to get the initial, we're going to get 10 times 0.4 minus 30 times 0.2. So that's the total amount of momentum. The one is plus, the other is minus. And then on the other side, we would get 10 times V1 final plus 30 times V2 final. We just say V1 final is the final speed of block number 1 and number 2. And so there's not enough information. And like I said, I was going to tell you that one of them was moving at a different speed. But so if you went within, okay, we need an energy, if it's an elastic collision, and we go, the kinetic energies are equal. Well, the kinetic energy of the first one is going to be 10 times 0.4 squared. The other one's going to be 30 times 0.2 squared. And then that's going to equal 1/2 times 10 times V1 final squared. And the other one's going to be 1/2 times 30 times V2 final squared. And now this is a system of equations. You can solve the first one for V1, plug it into the other. Yeah. So I don't exactly have the numbers for this because I didn't work it out because it wasn't my intention. But I will tell you this, that if you went with that assumption and you just went with it, you got the points for it. So again, I was pretty lenient with the scoring on that. But a lot of you forgot to answer the second part of the question, because the second part of the question said how much energy was lost, if any. So with my original question, you'd have to use those velocities and calculate the energies and look at the difference, and there would have been a difference. But what the answer should have been for all of you that said this, that went with this, part B should have been no energy loss. Because you assumed there was conservation of energy. So it should have been a really easy no energy loss. Now, a lot of you went ahead and calculated numbers. Many of you found really small numbers, and that was just because of the rounding. So when you rounded this and found whatever your V final were, there was a little bit of rounding issue. But really, part B should have just been a real quick no energy loss, because that's what you guys assumed for part A. Anyway, so there was number 7. 8 and 9, another set of conceptual problems. So for those, and again, I'm not sure which order they're in, but the one was the glass dropping on concrete versus wood. And really what I was going for was impulse. The concrete has much greater impulse, which means the force, that you get a bigger force over that shorter amount of time. There's not a long time for that force to dissipate. And so it cracks, as opposed to wood. The impulse is such as that force is spread out over a longer amount of time. And that's why it broke. So some of you talked about like stress and strain and elasticity. And that's true. The wood is definitely more elastic, which is what allows for that force to occur over a longer period of time. So it's cool if you go down that route, but make sure you include something about impulse, the fact that that force is being dissipated over a greater amount of time. Again, I think I was pretty fair with grading. I didn't take very many points off for that kind of stuff, but if you are concerned and are not happy with how I scored, just let me know. We can have a conversation. So there was that one, the breaking of the glass. And then the other one was, do you attract the sun more or less? Or basically, when do you attract the sun more? At noon or at midnight? And the answer is noon, because you're actually closer to the sun. And so you've decreased your R, which increases your gravitational force, which means you increase your gravitational acceleration. So, and I forget who it was. I think it may have been Max. Somebody said it doesn't really matter because the only difference is the diameter of the Earth. And yeah, in terms of actually computing it, you would see marginal difference. However, technically it is stronger. Like we are pulling on the sun more right now than we will at midnight. So, anyway, and then there was number 10. You guys really didn't like number 10, and in fact, very few of you even saw kind of where to go with this. But this is conservation of angular momentum. This is the exact same thing as the skater who pulls her arms in to go faster, right? We've got this star that's imploding, so it's changing its radius, which means, so it's changing its moment of inertia, which means it's going to be changing its angular frequency. So this is literally just a conservation of angular momentum. So we're going to have I initial omega initial equals I final omega final. And we're really curious about omega final. So there's our formula. Now in terms of I, it's a sphere. So the sphere, I of a solid sphere, is 2/5 mr squared. So in terms of the initial, it's going to be 2/5 mass times its initial r. So I'm going to call it Ri squared. The final is going to be 2/5 m r final squared, and then again times omega initial. And the beautiful thing is that a lot of this stuff just cancels out. So what we get for our omega final is the initial radius squared. So the initial radius was 7 times 10 to the 5th kilometers. You can convert it to meters if you want, but it's not necessary since the other radius was also given in meters. But it compresses down a lot to just 16 kilometers. And these numbers are actually plausible. Like this is the kind of size difference we see when stars actually implode. Okay, so we got that, and then we need our omega initial. Well, our initial omega, it does 2 pi in 30 days. So I'm going to go ahead and do it as radians per time period. If you went with revolutions, that's fine as well. So this is going to give us our omega. And then, of course, to get our period, it's just 2 pi over that. So the final period is going to be 2 pi over omega final. So whatever this number is, we divide it into 2 pi. So what we get is 1.56 times 10 to the minus 8 days. So it's gone down a lot. But that's because we changed our moment of inertia a lot. Again, skater brings her arms in, she spins faster. That's what happened here. This is such a small number that it probably doesn't even really mean anything to you. I converted it to seconds. That's 1.35 times 10 to the minus 3 seconds, which is also an incredibly small number. It ends up being 700 something, like 740 times per second. So this star that once took 30 days for it to spin is now doing it so that it spins 700 sometimes every second. So that's pretty incredible when you think about what the conservation of angular momentum requires. I will say in the real world, there is some mass lost. I just gave you that so that you didn't have to worry about mass and make calculations a little bit easier. But in the real world, that's actually part of it. All right, well, there was number 10. Again, it was just a conservation of angular momentum thing. And then number 11, you guys all did really well on that. You basically calculate the moment of inertia for the disk. You can then calculate what your alpha is, because you're going from 450 revolutions per minute to 0. And then once you got that alpha, you can multiply it by I to get your torque. And then your torque will get you to your mu. So most of you got it. Mu is around 0.482. There were a couple people that didn't convert to radians, left it as revolutions. And that'll get you off by 2 pi, which is fairly significant. Anyway, all right, so that was exam 1. I did get them graded, and they're in the grade book. Next up, of course, is quiz and more homeworks. I actually have a goal. I'm going to put it out here on record. We are recording. My goal is to have everything graded for you guys by a week from Wednesday. We don't have class on Monday. Next Monday, it's Memorial Day. So I'm going to use that in addition to this weekend to catch up. So that's my plan. We'll get everything back to you by then. Anyway, all right, so any questions on the exam? You feel okay with what I showed you?
Looks fine.
Okay, cool. So then what about homework? I know, Max, you started to say you had a homework question.
Yeah.
What would you like to look at?
So it was number 60 on the homework.
From which chapter?
15.
Okay, so number 60.
Yeah.
From chapter 15.
Number 60.
Yep. Okay.
Just making sure.
60, right? 60.
Yes.
60.
60.
Okay, so a mass is placed on a frictionless horizontal table. Spring, which can be stretched or compressed, is placed on the table. 5 kilogram mass is attached to one end. The other end is anchored to the wall. Equilibrium position is marked 0. Student moves it 4 centimeters, releases it from rest. The mass oscillates in simple harmonic motion. Determine the equations of motion. Find the position, velocity, and acceleration at time 3 seconds. All right, so does that sound like the right one?
Yeah.
Okay. So let's see what we can do about this guy. All right, so we're in simple harmonic motion. So that means that we know exactly Sorry, my book just collapsed on itself, so I lost the numbers. Let me pull it back up. But anyway, since we're in simple harmonic motion, we know exactly what this is going to do. We know that its position is sinusoidal, which means its velocity is sinusoidal, which means its acceleration is sinusoidal, right? And we even have the nice formulas for it. So if we go back and we look, we saw that position, and we can do this with sine or cosine, it doesn't really matter, but I'm going to use cosine because I'm a big fan. So we know x is going to equal a cosine of omega t plus phi. So then our velocity is minus a times omega times sine of omega t plus phi. And then our acceleration is minus a omega squared cosine of omega t plus phi. So those are the formulas that we need to plug in, we need to calculate. So basically we need to find a, omega, and phi. All right, so some things we know. Some other things we know when we're talking about the spring system. We know that omega is equal to the square root of k over m. So if we know k and m, we can get omega. Do you remember how we find a? Okay, so Victor said it's the change in x. Yeah, it's the greatest change in x. So it's going to be the greatest distance we get from equilibrium. And then phi, the way that we can calculate phi is by doing good old 2 pi over omega. So we can calculate that when we need. All right, so let's get the information again. So it says that the spring has a K of 100. Okay, so that's a given. So we got 100 newtons per meter for our K. We also know the mass. It says that we've got a 5 kilogram mass that's being attached to it. So that'll be 5 for M. So then it says the equilibrium position is marked at 0, and then a student moves the mass out to 4 centimeters and releases it. Okay, and we're releasing it from rest. So think about what's happening. So here's equilibrium. We pull it 4 centimeters, and then we just let it go. So we're not giving it any initial velocity. So it's going to start out at 4 centimeters, and then slide, and then come back, slide, and come back. So in this situation, then we know that A is that 4 centimeters. So I'm call it 0.04 meters. All right, so we're ready to calculate omega. We've got our A, and then we'll worry about phi in a second. But we good so far? Good to calculate?
Thumbs up.
Okay, I like the verbal thumbs up. All right, so omega then is going to be the square root of 100 divided by 5. So that's going to be the square root of 20, or 2 root 5. So then our position is going to be 0.04 cosine of 2 root 5 times t. And I'm going to leave it unfinished for just a second. We'll worry about phi. No, let's go ahead and take care of it. Okay, so what kind of phase shift do we need? Well, in this case, we don't need any phase shift. Why not? Why can't I just put the parenthesis there and not put a plus something? This is really testing your trig. What do you know about the graph of cosine? What happens at 0?
It's 1 away from.
Okay, so it's 1. It's the max, right? It's the maximum value. Well, we're starting with this thing fully stretched, right? We're giving it its full displacement at the start. And so since we're giving it the full displacement at the start, I'm going to use cosine. Alternatively, I might use minus cosine if I want to designate that the initial position was negative. But either way, if you're going to start at your max or min, use cosine, because then you don't need a phase shift. Okay, so there's our x. So then our v, of course, is the derivative of this. So it's minus a times omega. So that's going to be minus 0.08 times root 5. Again, I don't care about the specific number. And then that's sine of 2 root 5t. And then acceleration, when I multiply by that again, I'm going to get 20 times a, so minus 0.8 cosine of 2 root 5t. So there's the first part. The first part of this says determine the equations of motion. So boom. And then for part B, it says find position, velocity, and acceleration at time t equals 3 seconds. Well, now you just plug 3 in. So I'll let you do that on your own, but at this point, it's just a matter of plug and chug. All right, so do we feel better about that one, Max?
Yeah, thank you.
All right. So Victor, the negative 0.08 square root of 5 is the maximum velocity. Yeah, I guess technically it would be the absolute value of it. But yes, if you were to look at this, whatever that number is, that's the greatest speed that this block's going to have. And do you remember where that occurs? Where is it that you actually get greatest velocity? Yeah, it's at the equilibrium point. So as we're cruising through, every time we pass through the equilibrium point, we are going to max out our speed. It's going to be 0.08 times the square root of 5, whatever that number happens to be. And that'll be in meters per second. And similarly, the greatest acceleration is 0.8. And you get greatest acceleration when you're out at the extremes, when you're most stretched. All right. So any other homework questions at this point? Are you feeling pretty good about simple harmonic motion?
Yeah, it's not too complicated.
Yeah, and what's nice is it always follows the same form. So if you know you have simple harmonic motion, you can literally do what I did, which is just start by writing out your equations and then start figuring out what those missing pieces are. All right. Cool. Well, then we're going to continue our discussion that we left off last time. So last week, hopefully you remember that what we were looking at were waves. And specifically where we got was looking at standing waves. So what happens when we send a wave down a string? I just realized you guys are getting a horrible echo. So we send a wave down a string. It bounces back and just keeps, oscillating. So when it bounced back, we took those two waves, we added them together, and we got what was called a standing wave. So it was a wave where the particles, the amplitude of the motion, the vertical motion, was dependent upon where we were, in addition to what time was going on. So there was a time-dependent piece and a position-dependent piece. And the position-dependent piece we saw ended up giving us places where there was no vertical motion. And we called those nodes. And then the spots where we had maximum vertical displacement, we called those antinodes. And we saw that there was a relationship between where they were and the length of the string and the wavelength and all that. So let me remind you about that. Let me go back to the board and put some things that we saw last time. All right, so again, we're sending that good old sine wave down and it's bouncing back. So here's our string, but we send that wave down, it bounces back, and what we ended up getting was something that looked like this. So this would be a picture where it's got 3 nodes and the 2 antinodes. But this one, what we would see here is that string going back and forth, so it would look a little bit fuzzy, but we would see this sort of setup. All right, so how it ended up playing out, the equation for our position, our vertical position, was dependent upon x and t, and let me just kind of break it down nice and small. So it was 2a, where a was the amplitude of the original wave. So it actually gets twice the amplitude. But then there was a sine of kx and a cosine of omega t. And if you go back and you look at your notes, and I've got it backwards, it's totally okay, right? Where you got a sine times a cosine. It just depends which function you start with, whether you go with the sine or cosine. So hopefully this looks the same. If not, it still means the same thing. But the way that this played out was this 2a sine of kx. That basically gave us this piece right here. That gave us this wave. And then as time goes on, the cosine bit makes that change its amplitude so that it shrinks, goes to the other side, gets bigger, then shrinks, comes down, grows bigger, shrinks, and so on. So that makes any one particle just bounce back and forth. How far it goes, we got to figure out where we are. So we use the x to determine the amplitude at that specific place. And then this cosine bit tells us how it's moving up and down. Okay, so we got here, and then we started looking at where are those places of 0 amplitude. So we called those nodes. And we saw that the nodes occur regularly. So where they are depended upon the frequency. And so we saw that there was a relationship here. There's always a node at the ends. But then those nodes, they could only occur every half wavelength. So right here, every 1/2 lambda. And so from that, we found out what the acceptable lambdas are. And there were a whole bunch. So we had lambda sub n. And it was equal to 2L over n. So n, you can just let it be whatever you want. any integer starting at 0, not 0, 1. Obviously, you can't divide by 0. But then just keep going, and then L was the length of that string. So those were our acceptable lambdas, which then meant the allowed frequencies. We get the frequency by taking velocity and dividing it by lambda. And so if I call these, say, f sub n, it's going to be v times n over 2L. And so the v over 2L, this one, which was f1, we call this the fundamental frequency. Because then once you've got that, all the rest are multiples, right? We just let n increase from 1 to 2 to 3 to 4 to 5, and so on. And so then the last thing I showed you or reminded you about was that the speed of the wave on the string depended upon the tension and also the density. So another way that we look at this is that that fundamental frequency, it's equal to 1 over 2L times the square root of tension over mu, where mu is the mass density of the string. So this is where we got last time, which was looking at standing waves on a string. So what I want to do today is talk about sound. Let's talk about sound and how it behaves, how sound waves form. And then we'll kind of look at the same sort of thing about standing waves in tubes. So what makes things like musical instruments like trumpets and the like work. Okay, so this is where we're going. But let's first just start talking about sound waves. What are they? How do they work? Because they're a little bit different. Like you think about it, when I speak and you hear me, it's not like there's a string that's going from my mouth to your ear. And in this situation, it's even weirder because it's got to go from my mouth into the microphone on my device, sent data transmission to wherever you're located, then out your device has another sound, which then comes up. But even if we cut out all that middleman stuff, and you and I were in the same room, just talking, there isn't a string. There isn't this thing vibrating, except there is vibration. It's not a string. So here's how this works. Sound is kind of weird in that it's actually not a longitudinal wave anymore. It's a transverse wave. Okay, so you remember the difference, hopefully. Right, now we've got this motion. The motion that's involved is in the direction of travel. So let's say you're standing over on this side, and so the sound that's leaving me is moving this direction. So now instead of the wave going up and down, the wave's going to be going front and back. All right, so in essence, we've got some sort of particle that's going to be vibrating back and forth, left and right, as opposed to the string, right? The string we were moving up and down. Well, what is it that's moving? Well, it's the air particles. It's all of the molecules and everything that are actually in the air. And so not only is sound a transverse wave, it's what we call a pressure wave. So here's what goes on when there's sound. Okay, so this is my mouth. So we'll put some teeth here. No, that's going to look really, really bad. Okay, so here's my mouth, and we've got a wave coming out, right? Got a sound coming out. So here's what's going on. We have all these particles, right? Think about air, it's particles all over the place. And normally they're just kind of doing their thing. Now, when I start speaking, my vocal cords start vibrating. They start vibrating back and forth. So the part that's closest to me, this starts vibrating back and forth. So think about what's going to happen to the air particles. All the ones that are really close are going to get pushed. So now all of a sudden, there are going to be a whole bunch that are really close together. So I push them all together, and then I retract. And then the next vibration happens, I push a bunch together, and then I retract. And then I push a bunch together, and then I retract. And so what ends up happening is we start seeing a series of places where all the particles are really heavily condensed, followed by spaces of not much, followed by spaces of lots, not too many, lots, not too many. And so in terms of pressure, we have a whole bunch of places of high pressure. And in between those places of high pressure, there are places of low pressure. So if we were to draw a graph of pressure versus location, so this will be X and this is going to be pressure. Think about what we're seeing. We're seeing high pressure to low pressure. I'm not going to have it go to 0, okay? But it's going to go from high pressure to low pressure, back to a high pressure, to a low, to a high, to a low. And so you can see this is sinusoidal. And if we wanted to get it back down to just a sine wave or cosine wave like we're used to that goes through the axis, we basically would just have to find this middle spot. And then we could just look at what is the difference as we go up and down. Well, this middle one, this would just be the pressure. So I'm going to put atmospheric pressure. So like right now, if you were to, in your room, you had a barometer. That's the tool we use to measure pressure. But you read off a number, that would be this pressure. And then as I speak, or as that wave is coming out of your device, you are going to see that pressure go up and down. And it would go up and down this way. Okay, so instead of looking at it as pressure, what we like to do is look at it as change in pressure. So let me just do this real quick. Basically, what we're going to have is the change in pressure. So that's the going up or going down. Well, it's going to be some maximum change in pressure times cosine of kx minus omega t plus v. So this whole cosine business, that's the same as what we did before. That allows it to be a time and position dependent wave. But now it's a pressure change. So this whole cosine business is just because there's oscillation. And like I said, it's the vibrating of my vocal cords that are making that happen. A fun experiment sometime, you can actually do this since all of you guys are mic'd right now or are quiet. Just take a second, put your hand just right here on your neck, right under your chin. and talk a little bit, and you will definitely feel the vibration. You'll feel that vibration go through your hand. And so since you can feel it in your hand, the air feels it as well. And so we'll start vibrating. All right, so sound is also a wave. You can also think of it, though, as the individual particles going back and forth, like I talked about there. And if you were to look at an individual particle, it's going to move in a sine wave as well. Except we'd have to think about it as sideways. It's going to move to the right, and then it's going to move to the left, and then it's going to move to the right, and it's going to move to the left. I'm just pulling this down so we can see it as time happens. Physically, it's just going back and forth on my little red arrows. But if we make a time axis, it would turn it into sines and cosines. So the individual particles themselves also follow a wave. So sound, we can really think there are kind of two waves to it. The one is the wave of pressure that's working its way. And the other one is the actual oscillation of the individual air molecules. But other than that, everything else is the same as when we were talking about like a wave on a string. The K is the wave number. It's still found the same way. It's 2 pi over lambda. Omega, that's the angular frequency. And it's 2 pi divided by the period, or 2 pi times the frequency, right? And then phi is any kind of a phase shift that's necessary. So maybe we're not talking about starting at a maximum pressure or something like that, then we'd have to adjust our phi. All right, well, here's another fun thing that you can do. This works really well on your cell phone. So the next time you get a phone call or something, listen on your cell phone, but without earphones. Okay, so, you know, like if you get a phone call, put it on speaker, or if you're listening to something on Spotify, just play it and play it loud. But then what I want you to do is wherever your speaker is on your phone, I want you to hold it up to something that where you can feel it. So like against your face or something, or even better, put a little, put a piece of paper there. Actually, let me see if I can do this. Show you this example. All right, so I'm going to switch screens. So you're looking at me here. I'm going to take my cell phone. So we're going to lose the board here for a little bit. And I'm going to turn up the volume. Now, this is probably going to create some feedback. Let's see. Okay, yeah, the feedback might be a little bit too much for this. Oh, there you go, Victor. Yeah, why don't you play something for me? And actually, before I turn this up, let me just explain what I'm going to do. So I'm going to hold this, and I'm going to take just a little piece of paper, and I'm going to set it near it. And hopefully what you'll see is this thing vibrate because of the music. Okay, so I'm going to mute myself, but keep looking at this window. And then Victor, why don't you play something and unmute yourself?
Uh,
Okay, so I could definitely hear it, but it wasn't strong. It wasn't loud enough for me to actually show you what was going on. So, but trust me, next time you get a phone call, it works really, really well with a phone call. Put yourself on speaker and crank up the volume, and you will feel it. You will feel the air being pushed. You can also, if you've got a speaker, especially like if you've got a larger sound system, so not just a speaker in like a, in your computer or your phone or something, but you know what I'm talking about, like the big stand-up speakers. Those you can definitely feel the pressure as they go. So anyway, sound is a wave, and there's kind of two ways of looking at it, either as a pressure wave or the actual wave oscillation of the individual molecules of air. All right, let's take a break real quick. I need to get up and stretch, so I'm going to pause. All right, so let's keep talking about sound waves, and let's actually look at this pressure and see how that affects things like the speed of sound, because that's kind of where we want to go next. Is we know that it follows a wave pattern, but what we'd really like to be able to do is talk about the wave speed, right? We were able to talk about how fast a particle goes along a string. We want to talk about how fast can a pressure wave move in a medium. Okay, so that's our next goal here, is to figure that bit out. So let me go to the board again,
and we'll walk through this. So let's start here. Suppose that we've got a tube of gas. Okay, so you can even think like out of my mouth here, there's just like, we're looking at the tube of air that runs this way, but that's this. Now, what we're going to do is we're going to apply some pressure. So on this end, right now, you can kind of think of it as that the pressures that are pushing on both sides are equal. Okay, that's whatever the pressure happens to be, the air pressure. But if I talk and I start making sound, okay, so these pressures are the same. Now what we're going to get is an imbalance of pressure. So I'm going to call this one P plus delta P, where the other direction we just have P. And as a result, that means that if we were to think that there was some sort of a membrane here, some sort of a cap or something, that's going to get pushed in. And so now we're going to have our end in there because we've added some pressure. All right, so let's think about this in terms of forces. So pressure is force per area. So the force is pressure times area. So imagine whatever that cross section is. In terms of the forces, we're going to have P plus delta P times A, it's cross-sectional A. So that's the force pointing this direction. And then the force pointing the other direction, well, that's going to be the P times A. So there's our different pressure. All right. So now let's think about this in terms of the bit that's moving. It's going to move a certain distance. It started over here and moved to this position. So just think of that's all that air that just went. Okay, so how far that goes, that distance is your velocity times your time. So we'll look at this little distance right here in green. And I'll rewrite it over here. That distance, we'll call it x. It's going to be whatever the velocity is in the x direction times time. Okay, so we've got that. And now we're ready to kind of get to our speed thing, because you may remember that speed, when we looked at the speed of the wave, it was the square root of the modulus divided by the mass density. So if we go here, we're going to see that that velocity is going to be the square root of whatever the modulus is over the density. Now, since this is a volume thing, since this is air, that modulus is the bulk modulus, and its density is rho. So let's calculate the bulk modulus. So when we looked at the modulus, it was force per area. Okay, it's the force per area divided by the strain, how this thing actually changed. Okay, well, in terms of the force per area, if we look at the difference in the forces, it's just your delta P. And if we divide out the area, it's just delta P. So the bulk modulus, it's going to have on the top a delta P. Okay, so now we need to look at the volume change over the original volume. Now, in terms of the original volume, obviously, if we just think about a tube of air, like coming out of my mouth here, it's got infinite length, so I can't really think about it that way. So what I'm going to think about is, let's go to the point at which the particles aren't moving anymore. Okay, so everything on the right side of this is going to be stationary. Those are the particles that are far away, that don't experience anything because of the wave I'm sending out. Now, when I say the wave I'm sending out, this is the one pulse. So I'm continually talking, I make one noise and stop. And we watch that wave go. So initially, there's only going to be a set number of things that feel the pressure from that wave. Okay, so we think about the volume. Well, the volume change, how much we actually change the volume, is going to be x times area. Okay, so if that's x times area, we saw that x is equal to Vx times t, whatever that speed is. Then that means the top of the denominator is going to be a times v sub xt. All right, so then what we need to look at is the actual volume of this, which is going to be some other distance. Let me call it y for right now. So that distance. So go ahead and we'll divide that by y. But that y is also an area, or the volume, I'm sorry, is the y times that area. So we'll do a times y. Okay, so now that we're here, let's think about that change in pressure. Right, that change in pressure, if we think about this fluid, well, let's do it this way. So this y, that's some other speed times time, but that speed, that's actually the speed of the wave. That's our guy v. And so it turns out that this is delta p over a times vxt over a times v times t. So the A's cancel, the T's cancel, and we're left with V times delta P over X. And delta P over X, that change in pressure over X, when we go and we look at density, that's where the density comes in. So long story short, it turns out kind of what I'm doing is I'm working backwards. I'm showing you how B is equal to this. We get that as our velocity. So what's important to know is this fact right here, that the speed of a wave in a fluid, it's the square root of B over rho. So I just realized that I pretty much went around in circles. It's clearly one of those days. But this is how we can actually calculate the velocity of speed, or velocity of sound in a fluid. All right, so basically, if you have a more dense object, that's going to slow your velocity. So denser things have lower speeds of sound. Obviously, the other thing that will change it is the bulk modulus itself. But for example, the speed of sound in air, I put here V air, it's around 334 meters per second. But then if you were to look at the speed in water, so water is quite a bit denser, this speed is around 1480 meters per second. And you might go, but wait a minute, if it's denser, it's supposed to become a smaller V. But realize we changed the bulk modulus as well. Bulk modulus tells you how able something is to be deformed. And water, because it's incompressible, has a very large V. So it is kind of interesting that it depends not just on its density, but also its bulk modulus. If you wanted to compare something to air that would be, relevant or realistic, would be like, what if it was just, say, helium? So helium, like air, can be compressed, so its B isn't going to be that different, but its density is way less, right? Helium floats in air. So this one, though, if you were to actually look at its velocity, it's on the order of like 960 meters per second. And there you can really see the change in density. The decrease in density led to an increase in the speed. So it sounds very different. Sounds make different noises in water or in helium because of the fact that they're traveling at different speeds, right? So one of the reasons when you suck in helium and you hear a weird voice, part of it is this. But the biggest part is that it changes how tight your vocal cords are. And so it changes the frequency at which they vibrate. Anyway, all right, so there's your sound waves and what's going on there. But let's talk about standing waves with sound for a bit. Because now that we know how it travels, let's look at when we're in a pipe, what happens with sound and what we can get for standing waves. So this is going to be a physical pipe where this side is closed. So what we're going to do is we're going to send a wave through the air down here, and then it's going to reflect. Well, the same thing's going to happen that we saw happen on a string where we get a standing wave. So think about what happens at this reflected part. Anything that's up above is going to get reflected down. And so when we add those things, we're going to get a shape like that. All right, well, if we kind of continue the idea, what we're going to see is a standing wave that looks something like this. Now you got to be careful because this is a little bit different than what we saw before. Before, when I drew this, remember this was telling me the amplitude of the motion, and so we had that particle on the string actually going back and forth. But that's not what this means. This is a measure of the pressure. And so this is saying at this point in position, the pressure is going from a maximum pressure to a minimum pressure, but those delta P's are the same amount. But that change in pressure decreases until at this spot, there is no change in pressure. So the particles here don't feel anything. It's just as if there were no wave. Okay, so this is a measure of pressure. So here's what happens though with standing waves in air. In an air column like this, you're going to get antinodes at open ends. And you're going to get nodes at the closed end. So what I just drew here is not the fundamental frequency. The fundamental would look like this. Let me put in the first one. So we'd have to have an antinode out here and a node back here. So what we would see is this. So this would be your fundamental frequency. So the next one would look like this, where we put in one more node. The third one, see if I can draw this relatively decently. We're going to need to have a third node. I think this will work out pretty well. So this would be your third one, and so on. So notice that it's a slightly different construction, because with strings, we had nodes at both ends, and then we were able to create our antinodes otherwise. All right, well, what I want to do is let's look at the wavelengths. Let's look at the wavelengths here, and then let's look at the frequencies that we get, so we can figure out the fundamental frequencies of the sound in these tubes. Okay, so look at that first one. How much of a wavelength do we have over this length? This entire like that, and we'll say that this pipe has a wavelength or a length of L. Well, if you look at this, we're going from a node to an antinode, and that's actually 1/4 of a wavelength. So in the first situation, we've got lambda over 4 is equal to our length. So lambda is equal to 4L. That was this guy. This next one, we just added half a wavelength. The distance from node to node is half of a wavelength. So for that second one, we have 3/4 of a wavelength equals lambda, or a wavelength equals L. So lambda is 4/3 L. Now this next piece, we've got 2/2 and 1/4. So that's 1 1/4 or 5/4. And now our lambda is equal to 4L over 5. But hopefully you see the pattern. The acceptable wavelengths are all 4L, but then divided by an odd. And what that odd is, well, it just depends on which frequency we're in. The fundamental frequency, it's 1. The bigger ones, then it's 3, 5, 7, and so on. Okay, so let's write all this down. We'll make it nice and condensed here. So when we've got a pipe with a closed end, what we see for our wavelengths, our lambda sub n, it's going to be 4L over, and to get the right number, we would need to divide by 2n minus 1. So that would make it so that we get 1, 3, 5. So this is if we allowed all the different ends. But often what you'll see with these is where we just have, we just know that the ends are odd. And so they'll say like if we're going to talk about the 4th fundamental frequency, we wouldn't actually say that. We'd say the 5th one would be lambda sub 5. But regardless, we get this nice little pattern, the closed end, which then means the frequencies. Remember, the way that we find frequency is to take our speed and divide by this. We're going to get V times 2n minus 1 over 4L. So those are our fundamental, our different allowed frequencies. And the fundamental frequency, F1, the one that all others are built off of, is V over 4L. So this is a little bit different, right? It's a little bit different than what we've seen before, but it's built kind of the same way. All right, so I'm going to show you an example because I can. So what I have here is an empty bottle of the finest of the high quality root beers. And bottles, of course, have an open end and a closed end. So this is exactly the kind of situation that we're just talking about. Now, I am going to create a standing wave. I'm going to create a pressure wave. And the way I'm going to do this is by blowing air across the top. So hopefully you remember from our discussion with Bernoulli that when there's velocity, when air moves, it creates a change in pressure. So I'm going to blow across the top, which is going to change the pressure. That change in pressure is going to create a pressure wave and hopefully makes a sound. All right, so I know you've all done that at some point where you've taken some sort of a bottle and you've blown across it. And so that noise you're hearing, that sound you're hearing, that's the fundamental frequency for this pipe. It's got a length, right? It's got that length. Put that in for your L. The speed of sound, V, well, it's going to be something on the order of 331, 335, 330 something, right? The speed does change a little bit with elevation and also with humidity and things like that. So when I put up that number, I don't even remember what I told you, I think 334, it could easily be 330, 338, right? So somewhere in there is going to be what your actual speed is in there. Okay, well, anyway, you run those numbers, you get that frequency.
You can also do that with your hands.
Yep. Yeah, when you like cup your hands together and you blow.
Yeah.
Yep, it's exactly the same idea. But now it's a shorter distance, right? Because you're thinking about the top to the bottom of your hands. But you can create this with lots of things, but the bottle's a really good example. Now, here's what I'm going to do. So you heard this sound. Keep this sound in mind. All right, so think about how low it is now. What I'm going to do is I'm just going to take some water and I'm going to pour it into the bottle. Okay, so effectively what I've done, I don't know if you can see on the screen, is I've shortened the length of the tube by this distance. So I've decreased my L, which means I should have a different fundamental frequency. Okay, my V is still the same. The speed of sound is the same. But now when I blow, listen. Do you catch the difference?
Yeah, it was like a bit higher.
Yeah, this is higher now than it was before. So here, listen, I'm going to blow this one, then I'm going to drink it, and then blow it again. So this is with the shorter L. This is with the bigger L. So there is a considerable difference in the sound that we hear because we changed the frequency. So as you're drinking your high quality root beer, at first, you're going to have a really, really short L. So if you blow across the top, you should hear a high pitched sound. As you continue to drink and that lower goes and the level goes lower, the tone will also go lower. So changing the length changes the fundamental frequency, changes the sounds that we can hear. The other frequencies, again, those are harmonics like we talked about before, but they're just harmonics in this tube. So for musical instruments that involve air, that's how you can actually change the tone, is by changing the length. You can also change the pipe a little bit, and I'll show you what that means. But this is if the pipe has a closed end. Well, let's change that. Let's actually look at what happens if both ends are open.
Oh, real quick. This is also why, like, you know, the old classic, you hold the seashell up to your ear and you can hear the ocean. What you're hearing there is the sound that's coming in from external stuff, bouncing back and coming back, and it's creating a standing wave. Now that tube is twisted, right? If you look at the inside of a seashell, it's spiral, like a conch shell or something like that. But it's exactly this idea. One end is closed, the inside end. The other side is open, and you get certain sounds. So, fun fact, next time you're at the ocean and you pick up one of those shells, that'll explain what you're hearing. Okay, but let's look at now a pipe with an open end. So both of them are going to be open. Well, we already saw that we have to have antinodes at open ends. So the first thing we're going to see here, which will give us our fundamental frequency, would be this picture, where there's an antinode at each end and one node on the inside. There has to be a node. If there is no node, there is no wave, because it would just be whatever that pressure differential is the same throughout, which means no wave. So there's our fundamental. The next one up, instead of having one node in between, is going to have two nodes in between. So what we're going to get is something that looks like that. So there's the second one. And then the third one would have three nodes on the inside. So it would look like this, and so on. All right, well, let's see if we can build our frequencies here. So the wavelengths, the allowed wavelengths, this one, lambda 1. If we look at this, we've got half of a wavelength. Remember, node to antinode is a quarter, so I've got half a wavelength. So that means that my wavelength is twice the length of the pipe. All right, so for the next one, we've got 3/2 of a wavelength. I lied. It's not 3/2, it's a full wavelength. And so for this one, this lambda is equal to L, because it's a quarter plus a half plus another quarter. This guy, we've got a half plus a half plus another half, so 3 halves. So that tells me that lambda 3 is 2L over 3, and so on and so forth. So what we see for this one, so this will be pipe with an open end. So open ends. What we're going to get is that our lambda sub n, is equal to 2L divided by n. So it was 2L divided by 1, 2L divided by 2, 2L divided by 3, and so on down the line. So we've got 2L over n. Well, from that, we can get the frequency. So the frequency, the nth frequency, is going to be V times n over 2L, which makes our fundamental frequency n over 2L, or sorry, V over 2L. So it's a very different fundamental frequency when we've got a pipe that's open at each end. So then you might be saying to yourself, well, wait a minute, things aren't designed this way. There's always a closed end on these. That's not true. When you think of something like a flute, for example, flutes can actually have closed ends or open ends. And then other instruments like trumpets, those are actually open ends on both sides. I know we don't think about it like where the mouthpiece is. We think of that as closed, but that's actually an open end to that. That's where we're actually creating the wave. And so that's got open ends on both sides. So again, you want to change your sound. We can't really change the speed of sound. So the only thing we can do is change our length. And a great example of that is the trombone.
So you guys know the trombone. That's the instrument that has that big long slide, and as they play it, they extend the slide forward and back. And that one, what's kind of interesting is that they can change the length instantaneously and while they're playing. And so when they play, it'll start, say, with a higher note and then go down. Like it'll go, right? And so they're changing the length. By extending that out, they're changing the length because it's a big tube that's moving through all these, but you're changing the length of that tube. Don't think about bends. The bends don't matter. Imagine just taking that and stretching it out so that it's straight. That's the length that we're talking about. And so when you have a slide trombone and you pull it out, you're increasing the length by double whatever this distance is. And that lowers the tone. So all instruments are making use of these facts. Like organs, what's interesting about organs, pipe organs, is that some of their tubes will be closed, there'll be an end cap, and some will be open. And that allows for a much greater variety of different frequencies that can be played. So kind of interesting how that's done. Now, of course, with more modern music where we use electronic devices like electric guitars and synthesizers and things like that. Now we're using electrical impulses, and we're allowing those to vary. It's usually from some sort of a magnetic field. But then that oscillation is translated through the amplifier into oscillation of a physical speaker, which then makes the sound. So even modern music still comes back to that idea of vibration, because we have to have something vibrating to actually create that sound. So, oh, thanks, Victor, for my imitation of a trombone. I don't know if it was nice, but it was an imitation. So the other thing I just want to kind of convince you of is that sound is a pressure wave. You feel it. I don't know if you've ever been near like an explosion, and I don't mean, you know, like blowing up a building kind of explosion, or you know, movies kind of car explosion, but just even something as simple as like a firecracker, or if you've been in the chem lab and some things, you know, the pressure built up too much in your flask and it shattered or something, you feel the sound. You can literally feel the sound, and that's kind of what I was getting at with putting your face near your speaker of your cell phone. But if you ever have anything that's making sound and you were to put your hand on it, you feel the vibration, right? I live in Nevada, and in Nevada, you know, we have lots of open space and people like to have a lot of fun with things, including blowing stuff up, right? And so not too far from me is a place where big open space where people like to go and set off pretty big explosions. Now, I don't condone that sort of thing, because that's how you lose fingers and all that. But every once in a while, I'll feel it. I'll hear it and I'll feel it, and I'll see the windows shake a little bit because of the pressure that's being created by that sound. So sound is a pressure wave, which is also why you can't hear in space. And I think we talked about this. I think Bradley brought this up or something along these lines at one point. But sound cannot travel through space because there is no medium to experience that change in pressure, right? Like, think about what we're doing when I talk. These particles are moving back and forth, creating a series of low and high pressure spots. That pressure wave comes to your ear. You remove the atmosphere, there's nothing to go back and forth, right? It's a vacuum, so there's nothing there, which means literally you cannot send sound through space. So then you think, well, how are we still able to communicate? Because, you know, when Neil Armstrong and Buzz Aldrin were on the moon, 50 years ago, we heard their voices, right? Everybody knows the small step for man statement, right? Well, but that sound wasn't being transmitted as sound. It was actually being transmitted as a light wave. That light wave, well, okay, so Neil Armstrong says those words. There's a microphone in his suit. That microphone reads those pressure changes, translates them into an electrical signal. That electrical signal gets sent through space because electromagnetic waves, light waves, do not need matter, which is kind of weird, to be perfectly honest, because all other waves, we think of physical waves, there has to be something that moves. But for light, there doesn't. Nah, well, when you get to fourth quarter, you'll talk more about that. But anyway, so it gets translated into this electromagnetic wave, which then can travel through space, no problem. So it goes from the moon to the earth. So then we've got a satellite receiver, dish or something that receives that signal. And of course, the reason it's shaped like a dish is because it's parabolic, uses the reflective properties to concentrate the signal at one spot. We all remember that from pre-calc, right? But then that electrical signal gets translated back into an oscillation, and a magnet drives a speaker head to vibrate. And now all of a sudden that sound's coming out, and we hear small step for man, giant leap for mankind, right? So weird that sound, we gotta have some sort of medium for it actually to vibrate. So Victor, you said, so that's how our ears work? Yeah. So your ear, inside your ear, we call it the eardrum. The scientific name is the tympanic membrane, whatever. But it's inside your ear, and it's very sensitive to pressure changes. And so when I'm talking or whatever, and that pressure wave comes, it starts vibrating the eardrum. Okay, so that eardrum then, now this is where I'm not 100% because I'm not a biologist. My anatomy and physiology knowledge is minimal, but I'm pretty sure we also have those little bones in your ear, right? There's the what they call the hammer, anvil, and stirrup. Yeah, fun. But anyway, those things vibrate, or they catch that and start vibrating, and then they trigger the nerve, and then the nerve sends a electrical impulse into your brain. That brain then interprets that and goes, oh, that means the eardrum is doing this, which means I'm hearing whatever sound. So it's like, you think about when somebody talks, there's a part of their body that vibrates. That vibration carries on, right? Back and forth, back and forth, back and forth through the air until it reaches your eardrum. Your eardrum then vibrates, and your brain interprets that as the sound. So it's a pretty complex process, actually, which to me is also interesting, that biology, that animals and, well, I guess anything else that would feel sound, do plants register sound? There's some question whether or not that happens. But at least with animals, that through the eons of evolution have created ways of being able to register those pressure differences and interpret them as sound. So kind of cool. And then in terms of, this is also a question that often comes up here that I'm just going to start to address, but we need to talk about some other things first to really get to it. You ever notice how your voice sounds different when you actually hear it on a recording, on a playback, versus, what you hear in your head? And it's pretty drastically different, right? Like, it always throws me, and I hear this a lot because when I've got my earphone in, when I switch to the to my phone, now I am hearing my voice through the phone. It's weird for a couple of reasons. One, there's that time delay. I'm saying something and then I hear it a split second later. But it also sounds very, very different. I don't know about the rest of you, but I would describe it as my real voice, the one you guys hear, as opposed to my internal voice. My real voice is higher pitch than what I hear in my head. Is that true for you guys as well?
Yeah, for me it is.
Yeah.
Yeah, okay. So I kind of figured that that's a pretty common experience for everyone. But in my head, I hear it as a deeper sound. I'm not talking about those voices, Ralph. Yeah, when you've got the competing voices, it's probably hard to tell what's what. But so why does it sound different in your head? Well, that's because of the construction of your skull. I'll just give you the real quick version and then we'll get more to the point later. But your skull actually has holes in it, has cavities. Like, you've got the sinuses. You've heard, I'm sure, of sinus. The sinuses are like under here. And so those are holes. But then there are also some, I think, up in your forehead and all that. But again, not a biologist. Right? But I do know that there are little cavities and stuff in your head. Now, what will happen is you'll get resonance. And this is where you basically get waves that build upon themselves. You get standing waves. And they can create resonance, and it's that resonance changes the frequency, which then changes the sound. So when we get to resonance, we'll talk a little bit more about that. But there is a reason that it sounds different to you. Your voice sounds different to you than to other people, and it's because of the fact that they're not in your head. They're getting strictly those sound waves that are coming out without any kind of bouncing around in the cavities in your head. So anyway, but that resonance inside of your skull is kind of a big deal. It's one of the ways that dolphins are able to detect things. They use sonar, basically. They send out sound waves, wait for the bounce, and then they can use that to figure out how far away things are. But their skull is designed so that it's got like a resonance chamber in it. So it's actually been evolved over time to create resonance to really amplify that returning sound so that they can hear it better. Right? They basically send out a bunch of clicks just that kind of thing. That as they send those clicks out, they go, they bounce, they come back, and they can time it, for lack of a better way of saying it. And that gives them a good idea of how far away stuff is, and they know that where things are. So bats do the same thing, and blind people can do it to a certain extent. You know, they say when you lose a sense, your other ones get heightened. I do know, I have heard of blind people that can send out series of clicks and listen for the returns, the echo basically, and that helps them picture where stuff is around them. So pretty cool. All right, so I think I'm going to call it for today. It's 5 o'clock. I know we usually go a little bit longer, but we're doing fine. We're right on schedule. Everything's looking good, and I think this is a good place to stop. So, anything else we need before I hit pause on this guy?
No,